Hello guys, let's begin from where we left earlier in the chapter sound. This is the last video related to chapter sound. So let's begin with the first topic, sonic boom. So what is sonic boom? When the speed of any object exceeds the speed of sound, it is said to be traveling at supersonic speed. When a sound producing source moves with a speed higher than that of sound, it produces shock waves in air. The air pressure variation associated with this type of shock waves produces a very sharp and loud sound which is called the sonic boom. In this photo, we can see that this airplane, which is traveling much higher speed than the speed of sound in air, which is also known as the supersonic speed, is producing these shock waves behind it. These shock waves are very powerful. These are even capable of breaking glasses that are used in buildings. When such aircrafts which travel at supersonic speed passes near buildings, there are cracks that appear in the glasses that is used to make the buildings. Now let's move on with reflection of sound. Like light, sound gets reflected at the surface of a solid or liquid and follows the same laws of reflection. These are the angle of incidence is equal to angle of reflection. The incident wave, the reflected wave, and the normal to the point of incident all lie in the same plane. There's an easy experimental setup which determines that these laws in fact hold true. As shown in this figure, we need a wall that will reflect the sound on one side of the table and two tubes which will be used to see that angle of incidence and angle of reflection are equal to each other. What we do in this experiment is, this tube is kept fixed in its position and a clock is placed at the end of this tube. Now the second tube is rotated starting from 0 degree with this normal. We initially hear a faint sound of the clock ticking. Now as soon as we increase this angle, we find that when the angle of incidence, which is this angle I, is equal to the angle of reflection, which is this angle, let's say F, we hear the clock ticking the loudest. Now when we increase this angle of reflection F beyond this criteria, the sound again starts to become faint. Hence we say that angle of incidence is equal to angle of reflection in case of reflection of sound. Let's move on to echo. If we shout or clap near a suitable reflecting object, such as a tall building or a mountain, we will hear the same sound again a little later. Many of us must have encountered this situation when we go for a picnic near mountains. This sound which we hear is called an echo. The sensation of sound persists in our brain for about 0.1 seconds. To hear an echo, the time interval between the reflected sound and the original sound therefore must be at least 0.1 seconds. Now if the speed of the sound is considered to be 344 meters per second in air, the minimum distance of the obstacle from the source and back, that is twice the distance of the source from the obstacle, must be 344 into 0.1 meters, which is nothing but 34.4 meters. And hence, the minimum distance of the obstacle from the source, that is D, will be 17.2 meters for echo to be heard. Echoes may be heard more than once due to successive or multiple reflections. The rolling of thunder is due to the successive reflections of the sound from a number of reflective surfaces such as clouds and the land. Now similar to echo, we have something called reverberation. The repeated reflection that results in the persistence of sound is called reverberation. A sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value which is no longer audible. To reduce reverberation, the roof and the walls of the auditorium are generally covered with sound-absorbent materials like compressed fiberboard, rough plaster, or draperies. The seat materials are also selected on the basis of their sound-absorbing properties. Now we can also have many uses of this multiple reflection of sound. Let's see some of these uses. Megaphones are loud hailers, horns, musical instruments such as trumpets and shehnais are all designed to send sound in a particular direction without spreading it in all directions. Similarly, stethoscope is a medical instrument used for listening to sounds produced within the body, chiefly in the heart or lungs. In stethoscopes, the sound of the patient's heartbeat reaches the doctor's ears by multiple reflection of sound. Generally, the ceilings of concert halls, conference halls, and cinema halls are curved so that the sound after reflection reaches all corners of hall. So these were some of the uses of multiple reflection of sound. Moving forward, let's see range of hearing. The audible range of sound for human beings extend from about 20 Hz to 20,000 Hz. Some animals like dogs and children under the age of 5 can hear up to somewhere 25,000 Hz. Sound with frequencies which are less than 20 Hz are called infrasonic sounds, and sounds with frequencies higher than 20 kHz are known as ultrasonic sound. Now these ultrasonic sounds are of very much use to us. We have a lot of applications of this ultrasound. Let's see some of these applications. Ultrasound is generally used to clean parts located in hard to reach places. For example, spiral tube, odd-shaped parts, electronic components, etc. Objects to be cleaned are placed in a cleaning solution and ultrasonic waves are sent into the solution. Due to the high frequency of these ultrasonic waves, the particles of dust, grease and dirt they get detached and they drop out. The objects thus get thoroughly cleaned. Ultrasounds can also be used to detect cracks and flaws that are present in metal blocks. Here is an experimental setup that determines the defect or flaw present in the metal block. From one side of the metal block, ultrasound is made to pass through it, and on the other side, detectors are kept to detect this ultrasound. Now, as this ultrasound encounters a defect or a flaw, it gets reflected back, and on the detector on the other side of the metal block cannot detect it, and hence we can exactly locate the position of this defect and flaw and make the changes accordingly. Ultrasonic waves are made to reflect from various parts of the heart and form the image of the heart. This technique is called as echocardiography. One interesting medical application of ultrasound is the ultrasound scanner. Ultrasound scanner is an instrument which uses ultrasonic waves for getting images of internal organs of the human body. A doctor may image the patient's organs such as the liver, gallbladder, uterus, kidney, and etc. In this technique, the ultrasonic waves travel through the tissues of the body and get reflected from the region where there is a change in tissue density. These waves are then converted into electrical signals that are used to generate images of the organ. These images are then displayed on a monitor or printed on a film. Now this technique is called ultrasonography. One more medical use of ultrasound is breaking of stones that are formed inside the kidneys into smaller stones. These grains are later get flushed out with urine. Now sonar. Sonar stands for sound navigation and ranging. Sonar is a device that uses ultrasonic waves to measure the distance, direction and speed of underwater objects. Here's the picture which shows how sonar works. The above method is called echo-ranging. The sonar technique is used to determine the depth of the sea and locate underwater hills, valleys, submarine, icebergs, and sunken ships, etc. The technique that is used in this is a transmitter and a detector are placed near the bottom of the ship. Now this transmitter emits ultrasound. This ultrasound travels all the way down to the seabed and gets reflected from it. After reflection, this is again detected by the detector. Now, depending upon the time taken by the ultrasound to come back, the depth of the sea is measured. With this problem shown here, we will see how is it actually calculated. So the problem says a ship sends out ultrasound that returns from the seabed and is detected after 3.42 seconds. If the speed of ultrasound through seawater is 1531 meters per second, what is the distance of the seabed from the ship? Now the distance that is traveled is given by velocity into time. This 3.42 seconds is the total time taken by the ultrasound from getting transmitted to getting detected. Therefore, that distance it travels during this duration is, let's say, 2d, where d is the depth of the sea. Therefore, 2d is 3.42 into 1531, which implies d is 3.42 into 1531 divided by 2. This is 2618.1 meters. Therefore, the depth of the sea is 2.61 kilometers. The final topic of this chapter is structure of human ear. The figure here shows the structure of human ear. The pinna collects the sound from the surroundings, which is the outermost part of the ear. The collected sound then passes through the ordinary canal. At the end of the ordinary canal, there is a thin membrane called the eardrum or tympanic membrane. When the compression of the medium reaches the eardrum, the pressure on the outside of the membrane increases and forces the eardrum inward. Similarly, the eardrum moves outward when a rarefaction reaches it. In this way, the eardrum vibrates. The vibrations are amplified several times by three bones, which are the hammer, anvil, and the stirrup in the middle ear. The middle ear transmits the amplified pressure variations received from the sound wave to the inner ear. In the inner ear, the pressure variations are turned into electrical signals by the cochlea. These electrical signals are sent to the brain via ordinary nerve, and the brain interprets them as sound. So this is how the human ear works. With this, I end the topic on sound. Thank you.